In the last lecture, we saw how log Sobolev inequality is equivalent to this inequality called Sturm's inequality, and yeah, therefore, by showing log Sobolev inequality, which we have already done in the past, we have also obtained a proof for Sturm's inequality. Now, what we will do in this lecture is present a different proof of Sturm's inequality, and in turn, that will imply the log Sobolev inequality because these two are Gaussian log Sobolev inequality. In fact, these two are exactly equivalent. By the way, the presentation of this lecture and the previous lecture are based on the now article on measure concentration by Igal Sasson and Max Raginsky. It's one of the references mentioned for the course. Okay, so let's begin. So recall that for for a distribution Q, with differentiable density Q, okay, the we consider two quantities. The first quantity was the entropy power n of Q is given by nq equals to e to the power 2 by differential entropy of Q divided by 2 pi e. Okay. Here this HQ was, if you remember, this was just integral minus infinity to infinity qx ln 1 by qx dx. Okay, that's HQ. And the Fisher information JQ, this quantity is given by so since we assume that the density is differentiable, we can take its derivative. I think a better notation is this one. This is the derivative of we can take the density's derivative, therefore we can also take the derivative of its log. This is that function, the derivative of log of Q. Evaluate that function at x and take the square of it and take the expected value under Q of this guy. Okay, this is the Fisher information. Okay, so just a quick discussion on this Fisher information. The quantity, the random variable, well, actually the function, maybe the function Sx equals to is called the score function. Well, why is it called the score function? Because when you are computing the likelihoods and you're looking for maximum likelihood estimates, you often set this derivative to 0, and so you compute the score function and make it small. So this score function is used in maximum likelihood procedures, and from theoretical perspective, this score function is used for analysis. Okay, so this is called score function. One thing about the score function is that I mentioned this in the last lecture also. The expected value under Q of this score function is equal to, let's see, it's equal to integral minus infinity to infinity qx d by dx log qx dx, and this is integral minus infinity to infinity q prime x dx. So this is the derivative of qx here, right? Because derivative of log is 1 by qx, so that cancels, and this guy remains. Now this thing here, we under some simple uh, condition, we can take this derivative outside, and this integral is always 1, so this becomes 0. So this guy is a zero mean random variable, and therefore its variance under Q is equal to expected value under Q of S square X, which is exactly what we are calling the Fisher information of Q. It's the variance of the score function. Okay, score function is a zero mean random variable. Its variance is called Fisher information. Okay. There's a lot more geometric meaning that can be given to this quantity, but that's a little bit outside scope for us. This quantity, entropy power, on the other hand, is related to the volume of a large probability set, a set which has large probability under Q. Okay, and it comes up in, as I said, it comes up in handling lower bounds for Gaussian coding problems. Okay, so now that we know meaning for both these quantities, we want to show Stamps inequality directly. In fact, this inequality is quite old, and it has been studied thoroughly in information theory, and we'll give an information theoretic proof of this Stamps inequality. So towards uh, proving Stamps inequality, which is NQ JQ is greater than equal to 1, that's Stamps inequality. Towards this, note that the quantities NQ and JQ do not change. Q remain unchanged. If the random variable which is generated by Q, if we replace XQ with some scaled version of it, okay, because you can recover X back from it, and these quantity only depend on the distribution as such. It doesn't depend on exact values. They do not depend on, these quantities do not depend on these exact values. They are a function only of this distribution. So if you scale and translate, it doesn't change. Therefore, we can assume that the expected value under Q of X is 0, and that its variance or its second moment is 1. We can assume that because this is finite. We only want to show it for the finite case. That was the assumption throughout, and we can normalize by that second moment and make it unit second moment, and also we can translate to make it zero mean. Okay, we can assume that. So from here on we'll proceed with this assumption. These are the assumptions we make from here. Right. Okay. So under this assumption, note, so if you look at the divergence between Q and a Gaussian distribution, so this PG is the Gaussian distribution with zero mean and variance 1. So basically same mean and variance as this X. So this can be written as expected value under Q, maybe something more explicit. qx ln qx by gamma x. This is the Gaussian density dx, and this is equal to, this first term is just minus hq. That's how we defined hq. And this term here, we have seen this before. It's half log 2 pi half log 2 pi plus expected value under q of x square by 2. Okay, and so this is nothing but minus hq plus half ln 2 pi e, because expected value under q of x square is 1, right? But then this is nothing but half of ln 1 by n cube. So in other words, this 1 by it's half log 1 by entropy power is exactly the same as divergence between q and pg. Okay, this is just exactly the same as divergence between this q and pg here. Okay, so what is this guy here? So this is basically what we can think of as gap to Gaussianity. So think of this distribution. So Q is a distribution. We want to figure out how far it is from a distribution, a Gaussian distribution with same mean and variance as Q. And one way to measure the distance is divergence between Q and PG. And this divergence is exactly what we use to define entropy power. Entropy power is 2 to the power minus 2 times this divergence. That's what entropy power is. So gap to Gaussianity is related to entropy power. Okay. So with this observation, we actually recall now a formula for this gap to Gaussianity. So we recall a formula for gap to Gaussianity. Okay, and this is the formula due to Guo, Shamai, and Vardu in 2004. It says that so we consider a specific channel. So consider the problem of estimating x from by using observation y given by y equal to square root gamma x plus z, where z is a standard Gaussian random variable with the standard Gaussian random variable that is independent of x. Okay, so x can have any distribution. X is a real valued random variable, and we look at this observation y, which is some scaled version of x plus some noise, Gaussian noise. We want to estimate x from this noisy measurement about x, and we want to do this measure. We want to do this under a mean square error criterion. So for any estimator phi which looks at we'll use phi with y as input, and we'll get some estimate x hat. We measure the loss, expected loss, by the mean square error. Okay, by expected value. So we use mean square error, phi y minus x square. Okay, let MMSC minimum mean square error for x when this strength here is gamma. This gamma denotes the signal to noise ratio because the noise variance is 1. This is the signal variance is gamma. We can assume x is 0 mean. Okay. So this is defined as, this minimum mean square error is defined as minimum over all phi of this guy. And indeed, it is well known which function phi attains this minimum. Right? That's something that you learn in any basic statistics course or the detection estimation course in the EC department. That function which attains this is the conditional expectation. Okay, and once again, I emphasize that this is valid for any joint distribution here. In this case, we are putting this specific distribution where the distribution of x is arbitrary, but distribution of z is a Gaussian distribution. Okay, so we define this minimum mean square error this way. It turns out that there is a very nice sort of beautiful formula that characterizes gap to Gaussianity in terms of this MMSC function, and this formula is due to Guo, Shamai, and Verdu. I'll recall this formula here. So the formula says that the divergence between Q and standard Gaussian PG is equal to integral minus infinity to, integral half integral 0 to infinity 1 by 1 plus gamma minus MMSC x gamma. So integrate this thing over this, okay, where x is distributed according to Q. Okay, so this x here has distribution Q. In fact, there's a little bit of abuse of notation. This MMSC doesn't depend on x; it depends only on Q. So maybe I don't know which one do you prefer. So you can also think of it as MMSC of Q gamma. Okay, it depends on the distribution, not really the realization. Okay, so it's clear what this term is. What is this term? This 1 by 1 plus gamma. This term here represents the minimum mean square error for the case when x itself was a Gaussian with 0 mean and unit variance. Okay, then we can actually see that the conditional mean is a linear function, and it's the mean square error for that condition corresponding to the conditional mean. So it is the Gaussian. So it's very nice. So basically, the divergence between Q and Gaussian is the same as the difference between the minimum mean square error for the case when x is Gaussian and for the actual distribution Q, which is the distribution of x. This difference integrated from 0 to infinity. Okay. Okay. So with this formula, we will now use this formula to derive Stamps inequality. We had seen that half. So using this formula for divergence, so earlier we had seen that half log 1 by entropy power of Q equals to divergence between Q and PG, but this guy is equal to half integral 0 to infinity 1 by 1 plus gamma minus MMSC this d gamma. Okay. So now we have a formula for this half log entropy power, but there is this term MMSC x gamma which we still need to handle. Okay. In fact, another thing that we need, another component of the proof that we need is a lower bound for MMSC x gamma. Okay, and the lower bound that we use is this was the first component. This is the first formula we have, and now this is the second formula that we are deriving. It's a very popular lower bound. It's sort of a classic lower bound called the Kramer-Rao lower bound. We're using an extension of it, which 2 is by now sort of classic, and this is called Ventry's inequality. Okay. We'll derive this inequality later, but when applied to this specific case, Ventry's inequality says that this MMSC for estimating x in presence of Gaussian noise is at least 1 plus gamma jq. So a little bit of history. For mean square error loss, a classic lower bound on mean square error loss. A lower bound for MMSC means that no matter what estimator fee you apply, you can never improve over this mean square error. So classic bound for this is the so-called Kramer-Rao bound, which holds for all unbiased estimates, unbiased estimators fee, estimators for whose expected value coincides with x. Okay. Its extension called Ventry's inequality gets rid of this assumption of unbiasedness. And this inequality's Kramer-Rao bound typically entails Fisher information. Fisher information for the channel, the noisy channel under which you observe x, which is the Gaussian case here. So this gamma here represents that Fisher information for the channel. This part of the Fisher information, this J of Q, is the Fisher information for the distribution of the unknown x, the distribution of the prior. So Ventry's inequality in effect replaces bias with a prior. Okay, it doesn't have any condition of unbiasedness, but it works only with a prior. So for our application here, the prior is Q. So we have this Fisher information of the prior, that's JQ. And this part here is the Fisher information of the parametric family or the noisy channel, that is the Gaussian channel that we're using. Okay, that's what this Ventry's inequality is. We'll prove it later, but if you substitute this Ventry's inequality here, okay, what do we get? So by combining Ventry's inequality with the expression we had for gap to Gaussianity, we get, so gap to Gaussianity was just 1 by was half log entropy power, and we saw that this is 1 by 1 plus gamma minus MMSC x gamma d gamma, and this is less than equal to, I'll bound this from below, so I have an upper bound on the whole thing, 1 by 1 plus gamma minus 1 by jq plus gamma d gamma. Okay, so let's integrate this. The first term we can integrate, that's log 1 plus gamma, and in the limit 0 going gamma going to 0, this is 0. In the limit gamma going to infinity, we'll keep that part. So limit, this is an improper integral in the sense that in the limit these things will cancel. ln 1 plus gamma and this ln jq plus gamma minus limit ln 1 plus gamma by jq plus gamma. Okay, that's what the integral is. So in the limit as gamma goes to infinity, this thing is just 1. Sorry, this is, the log is outside. Right. So in the limit as gamma goes to infinity, this thing is just 1. So the log of 1 is 0. And as gamma goes to 0, this is 1 by jq. So that there's a minus log. So that's log jq. So this is exactly equal to half ln jq. Okay, so what have we shown? So therefore, ln jq nq is greater than equal to 0, which is the same as Stam's inequality. Okay, so in conclusion, This inequality comes up quite naturally once we use this formula in Ventry's inequality. In the remaining lecture, I'll prove this Ventry's inequality. This formula itself I will not be proving, and this is a sort of a slightly not long or involved proof, but it requires us to introduce too many terms, so I'll just skip it. But it's this paper, this Go Shamai Vardu paper on IMMSC. That this paper is easy to find and it has a very clean derivation of this formula. I think this is theorem 14 in the paper. By the way, this formula has been generalized by Vardu to divergence between Q and P. Okay, so this is divergence between Q and PG. When you look for divergence between Q and P, instead of having this term here, you will have MMSC under the assumption that the prior of X is P. That's what you get. That's the more general form. This and then it coincides with this Gaussian formula when that P is PG. Okay, so we use Ventry's inequality in the middle. Let's see how we derive Ventry's inequality. Ventry's inequality is the sort of the classic statistics counterpart for Fano's inequality because it provides some lower bound for loss function of statistical estimation. And this particular loss function that we get lower bound for in Ventry's inequality is the L2 loss function. The proof is essentially just the Cauchy-Schwarz inequality. Let me show the proof. So for any function phi, consider this function phi from R to R. Okay, and then look at expected value of phi of y minus x times the derivative. Let's look at the joint distribution of xy. This is the joint density of xy. Note that for our application this joint density exists. Okay, this x has the density p and then q, and then given density of x we have this Gaussian density gamma, so this joint density exists for our application, but the proof will give us for more general thing. Let's look at this expected value. We can divide into two parts: expected value of phi y minus expected value of x. Oh, I should be clear here that this derivative here is with respect to x. Okay. So it's not clear right now why I'm starting with this quantity, but you can see that by Cauchy-Schwarz inequality I can bring in the mean square error times something else, and that will be an upper bound on this quantity, and we want to understand this quantity, so I'm just computing this quantity first. Yeah, sorry, I'm not spending too much time on this proof. This is just a quick presentation of Ventry's inequality, but as I said, once you start with this particular function you will see that this is just an elementary proof, although it's not clear why we start with this function. Now we understand this proof quite well. The best proof is the one I have found is in lecture notes on information theory and statistics by Yi Hong Woo, and that proof entails sort of a variational formula for chi-square divergence. Okay, it just follows from that. Okay, but here I'm giving a self-contained proof using Cauchy-Schwarz inequality. Okay, so once you have this, what do we do? So this can be written as integral minus infinity to infinity phi of y, p of y. Remember, y is the output, but we are still doing p of y. And then minus infinity to infinity derivative with respect to x of log of p of x given y. dx and dy. This is the first term here. Minus integral minus infinity to infinity x derivative with respect to x ln pxy. Sorry, to bring in density of x also here. So this is again density of x given y dx dy. Okay, so when we look at the first term here, this derivative is 1 by px given y, and then derivative of px given y with respect to x. So that is minus infinity to infinity py integral d by dx of px given y, for any given y we can do this, dy. Okay, that's the first term. And then the second term is minus infinity to infinity. Again, I can do 1 by pxy, which cancels this pxy, and then derivative of pxy with respect to, so let me do the same thing, py integral minus infinity to infinity x okay. I'm just giving you the technical step without giving all the details. You have to carefully see when how you can expand this integral, what can you take out of the integral, what can you differentiate. All those things you have to take into account. Now this thing here is equal to, so now we look at each of these terms separately. So this first term here, this one here, you can take the derivative outside the integral, and then this integral is 1, and then the derivative is 0. So this can be formalized and it can be shown to be 0 under some conditions, some regularity conditions on this px given y. But the only thing you want to ensure is that you can take the derivative outside. So suppose you can do that, then this is 0. We've always been assuming these kind of things. The second for the second term, if you look at this guy, we can apply integral by part. So this is x px given y minus infinity to infinity minus integral minus infinity to infinity px given y dx. So once again, as we argued before, in the limit as x goes to infinity and as x goes to minus infinity, under both those things, this will be 0 because we have assumed that x has second moment bounded. But this guy here integrates to 1. Okay, and so this py also integrates to 1. So this whole thing becomes minus of minus 1, that's 1. So this whole thing becomes, first term is 0, second term is 1. The whole thing is 1. So that is what have we shown. We've shown that this quantity here, this inner product here, is 1. Therefore, by Cauchy-Schwarz inequality, Cauchy-Schwarz this 1 is less than equal to, so now we'll apply Cauchy-Schwarz. So you can take square of this guy, and note what the second term here was. The second term was this particular partial derivative. Okay, so this is the mean square error that we were after, and this is that second term that we have obtained. Let's look at this second term. This derivative here is this is d by dx log qx, because the distribution of x is q, the density of x is q, plus d by dx of p of y given x. Now y given x is Gaussian. Okay, so this is d by dx of gamma of y minus, no, sorry, same notation comes up here. Yeah, so it's the Gaussian density of y minus root gamma log of this x whole square by 2 divided by root 2 pi. So when we take this derivative, we will just see that we get y minus root gamma x times root gamma. So this whole thing here, this can be seen to equal expected value of this mean square error times expected value of this derivative plus, now what is this guy here? This is root gamma into y minus root gamma x x, yeah, that's what it is, and whole square. So once again, if we just look at this quantity here, this is gamma ln qx plus root gamma z, the noise, whole square. But x and the noise are independent. So this expected value here is equal to the expected value of this qx whole square plus gamma expected value of z square. Because these two are independent and z is 0 mean, so they are uncorrelated. So this remaining term is 0. So you get just this. Okay, but z square was a 0 mean unit variance Gaussian random variable, so this thing is just gamma. Therefore, this whole term becomes expected value. This is my first term, the mean square error, times times this term here, which you can recognize as jq plus gamma. Okay, so to conclude, this mean square error for any phi exceeds 1 by jq plus gamma. So this is the Ventry's inequality. Okay, this is the Ventry's inequality, and in fact, these calculations are more or less general, hold for any distribution. The Gaussian part was not so important here. The place where we used the Gaussian part was this last step. Otherwise, you'll have the conditional distribution here, and that conditional distribution, same kind of derivative needs to be taken for the conditional distribution with respect to x, the input, and squared, and then taking expected value, and that last thing is called the Fisher information for that conditional distribution too. So it would, the general form is this JQ, the Fisher information of prior, plus the Fisher information for the channel or the parametric family that you're working with. That's the classic form. In this specific case, that Fisher information is gamma. So this is Ventry's inequality. So this completes the proof of last component that we used in a proof. So just a quick summary. So we started with observing that divergence between Q and PG, the gap to Gaussianity is half log NQ, half log 1 by NQ. And then we used this nice formula for gap to Gaussianity. And then this formula involves a minimum mean square error term, which we bound using Ventry's inequality. And then we evaluate the formula to get half log Fisher information. And when we combine terms, we obtain Stamps inequality, namely JQ times NQ is greater than or equal to 1. Okay. And in the middle, we use Ventry's inequality, which we proved. All right. So this is what I wanted to cover in this part. We saw that we saw that log Sobolev inequality is equivalent to Stamps inequality, and then we presented an alternative. We presented a proof of Stamps inequality, which in turn gives an alternative proof of log Sobolev inequality. In the next lecture, and maybe even the lecture after that, we will see connection of log Sobolev inequality to another very interesting class of inequalities, namely strong data processing inequalities, which in turn are related to hypercontractivity. So that's what we will see going forward. See you in the next.